Right, so fun begins. First problem set is posted, and we will have problem session on Friday. They're now in room 5 at 10 o'clock. Okay. We'll do a little bit more work at the board this semester, since we'll have easier board space to do that. So that's the plan. I had forgotten to send out email about office hours, so I will do that this afternoon to make sure that there's a time for all of us. All right. Very good. So, last time we were tying up one loose end that we didn't treat last semester that is extremely important in the main subject of this semester, which is the main subject of this semester is about the structure of matter. And when we are thinking about atoms and molecules with multiple electrons or multiple atoms, the total angular momentum of the system is an extremely important way in which we characterize the system. So, what do we mean by the total angular momentum? Well, so what we discussed is we considered the situation in which we had two angular momenta. They could be, for example, the spin and orbital angular momentum of an individual particle, or they could be, say, the spins of two different particles that are going to add together to become the total spin of the system. And generically, when we're talking about the generic angular momentum, we typically call it J. So the Hilbert space that we're restricting our attention to right now is the Hilbert space associated with these two angular momenta. And it is thus the tensor product space of the Hilbert spaces associated with each angular momentum. Okay? And that Hilbert space has this dimension, the product of the dimensions of the individual Hilbert spaces, each one of dimension 2j plus 1 in space 2j1 plus 1 and 2j2 plus 1. And there are thus observables that we're interested on the joint Hilbert space. So the total angular momentum of the system is the sum of the angular momenta vector operators for the two angular momenta, which is really just it's a shorthand for this, right? It's angular momentum on subsystem 1 and the identity operator on subsystem 2, etc. But we often don't write out that unless we want to emphasize something about the tensor product. We just have to keep in mind that operators on subsystem 1 all commute with operators that act on subsystem 2. Okay? Right. And we showed last time that this total angular momentum operator satisfies the expected commutation relations of angular momentum, and thus it is the generator of rotation on the joint Hilbert space. Okay? If it satisfies those commutation relations, then it is the generator of rotations. The total angular momentum commutes with the total angular momentum squared of each of the original ones. That's kind of obvious because we are restricting our attention to the space is made up of only things with a particular total angular momentum. Let it work out algebraically. As well, on the other hand, the individual projections on an axis, for example, the z-axis of 1 and 2, do not commute with the total angular momentum squared. Okay? What does commute only is the total. That is to say, this is negative of this. When you add them together, you get 0. But individually, they are not 0. Okay? So what that tells us is that there are two ways of course, there are many, infinite number of ways we can define a basis on the Hilbert space, but there are two kind of natural ones that arise in thinking about rotations. Okay? In your homework, you have another example of a representation for two, for example, spin 1/2 particles. The Bell basis is a very important representation we use all the time in thinking about quantum information theory, but it's not one that naturally arises from the theory of rotations. It arises in a different context. Okay? But when we're talking about rotations, which are the important thing in the context of spherical symmetries and such, these are the natural bases to think about. We have the so-called uncoupled representation. That's the representation we'd have written down from the beginning if we didn't think hard enough. It's a tensor product space, so that by definition, that is the space spanned by the product vectors of the basis vectors for each of the Hilbert spaces, right? And this set of states are the eigenstates that are uniquely specified, or the states in Hilbert space that are uniquely specified as the simultaneous eigenstates of this complete set of mutually commuting operators. Now, I heard a little chatter before class about how do we know how many operators we need to specify the space. Remember, we discussed this a little bit last semester. Commuting operators are related to conserved quantities. And the question is, how many conserved quantities do I need to specify something? How many degrees of freedom are there is really the question. Okay? So each angular momentum kind of lives on a sphere. So each one that kind of has 2 degrees of freedom. So you need 2 operators to specify a single angular momentum. If I have 2, then I need 4. So I need 4 mutually commuting operators to uniquely specify the state. Okay, so that's one set. Alternatively, this is a set of mutually commuting operators that uniquely specify the state. These guys commute, and this commutes with this, and this commutes with this, and these guys commute with each of the total JZ. Okay? And this representation we call the coupled representation, and the vectors are called the vectors that span the space are the coupled basis. Okay? So they're specified by these 4 quantum numbers, which are the total angular momentum quantum number, the total projection on the z-axis, and of course everything is always got J1 and J2 because their space is restricted that way. Yes?
So you're free to use either one. It doesn't. There's not certain situations where you have to use one or the other.
Of course, we can always use any basis to represent the state. We can always expand the state in any basis we like. On the other hand, as you know, certain bases are more natural to use in the context of a certain physical situation. So, for example, I haven't said anything about the Hamiltonian, right? So if we're talking about some particular interaction of particles, like say the interaction of an electron and a proton in a hydrogen atom, it might be the case that the good quantum numbers are the coupled representation. And there may be other cases where the good quantum numbers are the uncoupled. What do I mean by the good quantum numbers? What I mean is they are the ones that correspond to the commuting with that Hamiltonian. Okay? So we will see that in a few lectures from now, that when we, for example, couple the spin of the electron to the spin of the proton in the context of hyperfine coupling, then the good quantum numbers are not the spin projection of the electron and the proton, but in fact the joint projection and the total angular momentum. So which representation you use depends on the physics.
So like if they're interacting in some way, maybe the coupled is better?
Exactly.
Okay, okay.
Yes, exactly right. Yep. Okay, good. As we were just saying, the two representations span the space, and so I can always expand one basis vector as a superposition of the others, right? And these expansion coefficients have a name. They're called the Gordon coefficients, or Gordon. It's got the A in it. Yeah, we'll be studying them a lot a little bit later in the semester. Okay? But two important properties of the Clebsch-Gordon coefficients. These coefficients vanish unless these two conditions hold. The m quantum number associated with the total projection must equal the sum of the two projections. Okay, that is to say, the total JZ is just the sum of JZ1 and JZ2. So the m quantum numbers just add that way. Okay? The total angular momentum quantum number can be anything between the sum of the two total quantum number and the absolute value of the difference of them. That's known as the triangle inequality because it looks kind of classical, right? The magnitude of this vector can be as big as the sum of those vectors, or the magnitude can be as small as the magnitude of the difference of those two vectors, right? But you should be careful because, of course, this is not exactly the right picture, right? Because the magnitude of J is the square root of J1, right? Because the eigenvalue of J squared, so that the actual magnitude is this, right? And the square root of J2 plus J1. So how those adds up, it's not a continuum of things, but it is bounded in this way, as we kind of proved last time. And what that means is that the total angular momentum quantum number ranges in integer values, so integerly. So I can have the total J, let's just assume J2 is bigger than J1, or equal to. The smallest it could be is this. The biggest it could be is this. And it could be any integer in between. It's quantized, okay? The total angular momentum quantum number is quantized. It's not a continuum of possible values. All right. One thing I guess I could say relative to these two things is that there's one state, there's the so-called stretch state. I'm stretching. The stretch states are the states where I have the maximum possible value, which is J, or I'm sorry, J equals J max, is J multiplied state 2, and N equals N max equals the same thing. So that's the state which has the maximum total angular momentum and the maximum projection on that. There's only one way to make that out of the product basis. No other state, because M1 plus M2 has to equal N, right? So that state is this state. Okay? And similarly, if I have the minimum value here, plus or minus, plus or minus, plus or minus. Okay, so those states are the same in both representations. There's only a unique state, that is the stretch state, but every other state in the coupled representation is a superposition of states in the uncoupled representation. All right? Okay. Any questions about this so far? All right, let's continue then. what we were talking about in the last 5 minutes of the class was just an example of 2 spin 1/2. Okay, so we're adding the total spin. Okay, so here I'll call J1 S1, right, which I could write as 1/2 sigma. And same thing for 2, particle 2. Okay? And the total spin, that's 1 plus S2. Okay? Of course, density, identity, etc. Now, the uncoupled basis well, again, when we're talking about here, so here, S1 and S2 are, which is J1, J2, they're both 1/2. Okay? Typically, we don't, so if we're restricting our attention, we know that the 2 particles have spin 1/2. We don't have to write that. For each, what we have is a basis of spin up and spin down. This is really the state 1/2, 1/2, and 1/2 minus 1/2, right? Tensor with itself. That's to say, the uncoupled basis is up, 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 down, down, up, and down, down. Right? That's a shorthand for the tensor product of this with itself, the tensor product of this with that, etc. Okay? Alrighty. So now, let's talk about the coupled representation. So if I think about the coupled representation, first question for you is, what are the possible total spin quantum numbers of the system? That's to say, what is the total J, in this case the total S quantum number, which follows from those rules?
0 or 1?
Right, how do you get that?
The absolute value, J1 minus J2 and J1 plus J2.
Right, so this is between this and this, right? In integer steps. So the lowest it could be is 0, and the biggest it could be is 1. In this case, that means there are only 2 since they go in integer steps. I can have the total spin quantum number either be 0 or 1. Okay? And from this, it's easy to see, of course, that this is this subspace. So this is, I'll call this H0 tensor, or now. So I have these 2 subspaces. This guy has dimension. What's the dimension of this space?
2.
1, 2.
No, sorry.
It's a spin 0.
1?
1, right? Because only m can be 0, right? And this guy has what dimension?
3.
Yes. And so 3 plus 1 is 4, and that's good. Okay. All right. So in principle, we could just, ask Siri or Mathematica or something what the Clebsch-Gordon coefficients are. I think Siri knows that in iOS 8. Kidding. She might. I'll test that later. But we can look up the Clebsch-Gordon coefficients. But we can do this in a kind of brute force manner by just diagonalizing the set of operators that define the coupled representation. Okay? So in the coupled representation, we have, well, and let's go back over to this board for a moment. These are the operators, right? So now we have the total S squared, the total SZ. These are automatic, we don't have to do anything. So it's really, we have to simultaneously diagonalize these two observables. We have to find the basis which simultaneously diagonalizes those, right? Now, so let's diagonalize the total S squared and the total SZ. Okay? Now the total SZ is already diagonal in this basis, right? Because this commutes with S1Z and S2Z, and these are eigenstates of that. So if I were to write a representation of this operator in the uncoupled basis, ordered as I wrote it, okay, then what are the diagonal elements here? Well, that's the sum of this. That's a half plus a half minus a half minus a half plus a half, and minus a half plus minus a half, right? So that's, and everything else is 0. So that's diagonal, but there's a degeneracy here, okay? There's a degeneracy there, which means specifying the SZ quantum number, the total SZ quantum number, does not uniquely specify the state. Because there are two states that have the same eigenvalue, which is why we need a second operator to mute. If you remember, you had a block diagonal, and then you have to diagonalize again within the block. Okay? So now let's write down what the total, we have to diagonalize. The hard part is this. It's not that hard, but that's the more challenging thing. We have to diagonalize the total S squared. So we have to, we want to find, right, the matrix representation of S squared in this basis and then diagonalize it. Okay? So, how are we going to do that? Well, to do that, we say S squared is S1 plus S2 squared. So that's S1 squared plus S2 squared plus twice S1 about S2. 1 and 2 commute, so I can just write it like that. Okay? Glad you still have your job, Jesse. Thank you. Right, so we want to write a representation of this. First of all, it's easier always when dealing with spin 1/2 to deal with the Pauli operators. So I'm going to factor out the 1/2, and this becomes then 1/4 sigma 1 squared plus sigma 2 squared plus 2 sigma 1 dot sigma 2. Okay? Factoring out the 1/2. We already got rid of the H bar. That's why they're small letters. Right. So now I ask you, what is this operator? It's 3, right? Because it's sigma x squared plus sigma y squared plus sigma z squared. And each one of those is the identity, right? This is sigma 1x squared plus sigma 2. I'm sorry, sigma 1y squared plus sigma 1z squared. And each of the Pauli matrices is square root of the identity. So that's 3. So we get on this 3/4 times the identity plus 3/4 times the identity. Of course, we could have gotten that a different way. We could have gotten that as s times s plus 1, because this thing lives, or s1 times s1 plus 1, each one lives in that, and that's 3/2, or 1/2 times 1 plus 1/2, which is 3/4, so it works out. All right, now what about this? Well, this is equal to 1/2 sigma 1x tensor sigma 2x plus sigma 1y tensor sigma 2y plus sigma 1z tensor sigma 2z. Right? That's what that means. That's what that dot product means. All right, so now we want to write a matrix representation of this operator. Oh, there's a factor of 2 actually, it wasn't there. 2 times that is 1/2. How am I going to write a matrix representation of this operator in this basis? Well, I know this part is easy, right? These guys, we know what they do. They're plus or minus 1. But what about the sigma x's and sigma y's? How do we deal with, when we want to deal with angular momentum, where we write bases in terms of quantum numbers relating to z projections? These aren't operators which have simple action as in terms of eigenstates. So what do we do? Numbers.
In terms of other operators.
Which ones?
J squared minus s squared, or sigma 1 squared.
That would kind of get us back into a circle, I think, in that case.
Is it sigma plus or minus?
Exactly. Always deal with the raising and lowering operators, right? That's what we got. Yeah.
Just a quick question, so those identities, are they 2 by 2s or are they
Yeah.
4 by 4, huh?
Well, okay, so this is good. This is, of course, this tensor,
Okay.
this on 2. So this is really, you know,
Okay, thank you.
that, so yeah, it's buried in there.
Okay.
Good point. This is a 2 by 2, but this is always tensor, the identity on the other guy. So it's a 4 by 4. It's acting on this 4-dimensional Hilbert space. So we have the raising and lowering operator. So you'll recall that sigma x is sigma plus plus sigma minus, and sigma y is minus I, sigma plus minus sigma minus. Everyone remembers that.
Should it make a 1 over root 2 there?
No, that's what it is. I know there's all these stupid factors of 2, but that's what it is. Because you remember that s plus is equal to sigma plus. Remember that? Maybe. And s plus is sx plus isy, which is 1/2 sigma plus I sigma y. And then you add them up and you get a value. Everyone remembers that, because we didn't forget a thing from last semester. Right. Okay, so with that said, we can rewrite this, if we plug that back in with all the tensor products, as twice sigma plus tensor sigma minus plus sigma minus tensor sigma plus. That's what it comes out to be when you plug that in. Okay, the 2 i's, give a minus sign, you do a little bit of algebra, do a little dance, and that's what you get. Okay? So now we can, this is sigma plus on 1. If I write it this way, I don't really have to write the 1 and the 2. The guy in this is the 1, and this guy is the on 2. Okay? I could just call this ZZ. That's often what we do. All right, so now we have to write a matrix representation of this in this basis. So let's look at the action of S squared on up. Okay? So that's equal to, this is 3/2 times the identity. So the action of this on this is 3/2 on that. What is the action of these operators on this state? Well, sigma minus turns this to down, but sigma plus, what does it do? Annihilates it. So these guys will annihilate, and then I have this. And what's that value? So that's 1/2 times the sigma z times sigma z. And what's sigma z on spin up? +1, right? Because we got rid of the 1/2. Right? So this is 1/2 +1 +1 up. So that's equal to 3/2 plus, so that's 2. Okay. Now, is that a surprise?
Yeah.
No?
Well, what would we, if this is a stretch state.
So it,
A stretch state, when it lives, has a definite total angular momentum. And that total angular momentum is the sum of the two. This guy either has, if it's an eigenstate, it either has total spin 0 or total spin 1. Right? This guy has total spin 1. And what's the eigenvalue of that? S times S plus 1. That's why it's not a surprise, if you know what you're looking at. Right, so this is S, this is S times S plus 1, where S is 1. Okay? And similarly, on the down state, this is a 3/2 plus 1/2. Minus 1 times minus 1 is also plus 1. So this is also 2. And that kind of made sense. These two states, the stretch states, were not degenerate, right? So we really didn't need to think about this subspace. We already know how they're represented. They're the same. They're both, these are eigenstates of the total momentum squared. Yeah.
and up, down, and down, up to just be 1, right?
Well, let's do that. Let's do it. What happens to these guys? So now let's see what happens when I act this on up down. Okay. So this, let's write it all out. This is 3/2 the identity plus, what do we got there? 1/2 sigma z plus tensor sigma minus plus sigma minus tensor sigma plus, all acting on up down. Yeah. Right? So that's equal to 3/2 up down. This is what? What's the next piece?
Minus 1/2.
Minus 1/2, thank you. Does nothing. Up down. What about this acting on that? 0, right? And what about this acting on that?
Switches the.
Switch it, makes it to down up. Right? And so putting it all together, we get 3/2 minus 1/2 is 1. This is up down plus down up. And if you do the same algebra on the other state, in fact, you get the same thing. Okay, just go through it. So now, what is the representation of S squared in this basis? Well, it's block diagonal, right? That's to say, it's diagonal here, it's got 2 over there. These two guys, I got 1, 1, 1, 1, and 2. And then zeros everywhere else.
Should be just spelled down the last. Okay.
Sorry, down, down. Yes, pardon me. Thank you. Right? So, as expected, I need to diagonalize in this subspace, because that's where the degeneracy lies. Okay? So, that's an easy thing to diagonalize. First of all, I can write this as a half, so 1, 1, 1, 1, this matrix is that. You always write it as in terms of pseudo-Pauli's, right? And I just have to diagonalize this guy, which has eigenvalues. They're like the eigenvalues of sigma x, which are symmetric and anti-symmetric combinations. So the eigenvalues of this matrix, this has eigenvalues plus or minus 1. So the total eigenvalues of the system S equals 0 or S equals 1, where for S equals 1, the state is the symmetric combination. And S equals 0, it's the anti-symmetric combination. If you want, you can write the characteristic polynomial, diagonalize it, but for 2 by 2s, you can just look at it. Okay? So those are the 2 eigenvectors of this matrix. Okay? And then these are also eigenvectors. So the eigenvalues here is S. The eigenvalues of that matrix, S squared, are 0 and 2, right? And that's 1 times 1 plus. Okay? So, what do we have here? What we have in the coupled representation are the following. There is one state, as expected, with S equals 0. So the state S equals 0, M equals 0, is this combination. And there are 3 states with S equals 1. There's a state where M equals 1. That is the state up. There is a state where n equals 0. That is this state. And then there is a state where n equals minus 1. These were the 2 states we found as the stretch states. They are the states which have the maximum total angular momentum and the maximum or the minimum projection. They are just product states. The states that are not the stretch states are superpositions. And in this case, they're just the symmetric and antisymmetric combinations of the 2. Okay?
Last one be S equals 1.
It should be S equals 1 indeed, thank you. So, this is very important, especially in the theory of chemistry, when we think about the Pauli exclusion principle and the pairing of electrons and such. We'll get to that. This combination of electron spins, this is the famous singlet and triplet. So this is a way, this is the brute force way to find the coupled representation in terms of the uncoupled representation by explicitly writing out the operators that define the mutually commuting sets and diagonalizing them. You'll have an example for that, you have an example in the first problem set. But most typically, when we do this, we just look up the Clebsch-Gordan coefficients. In the old days, you had to get a little book, and it was like this tiny, but now, yeah, Siri usually. All right? Any questions? Yeah.
So is this, that's not enough to identify all the states either though, because there's degeneracy there too, am I understanding that correctly?
No, there's no degeneracy.
So.
There were two unique, there's an S equals, so these two quantum numbers, okay, so you need both to simultaneously diagonalize S squared and SZ. So if I diagonalize S squared alone, you're right, there's a degeneracy, right? There are two different states here. In fact, there are three. But to uniquely spec, because there's this guy,
We need the M2.
this guy, and then we need the total M.
Okay.
So, which is the eigenvector of SZ. So we need two quantum numbers. The total quantum number S and the total projection on, say, one axis is the axis M. Those two together uniquely specify the state. But any one of those does not. If I specify only the M quantum number, these guys are degenerate and these guys, and then I have these two, right? If I specify only the S quantum number, then I got these three and that. So I need both quantum numbers. All right. We are going to return to this later in the semester when we more formally study the theory of SU2 and groups. But we do need this if we want to kind of get the basic picture of structure of matter when we start talking about things like the hydrogen atoms, spin orbit coupling, and hyperfine coupling. We needed this little piece. But now I want to turn my attention to something else. Another important foundational piece in thinking about the structure of matter, and that is the forces. So in our discussion so far, this academic year, when we talked about the Schrodinger equation and we included a potential, we did it phenomenologically. We just said there's some potential, and we just wrote it down, like a harmonic potential for the simple harmonic oscillator. But when we want, the question is, how do we get those Hamiltonians from some discussion of fundamental forces? Okay? So, in particular, well, if we're talking about normal matter, atoms, molecules, condensed matter, there's only one force that matters. Gravity is irrelevant, so tiny at the scale of the masses of electrons and nuclei, we could just forget about gravity. The strong and weak forces are nuclear subatomic forces, so we're not talking about that in this class. So there's only one force that matters, and that's electromagnetism. Okay? So what we need to talk about, what I'd like to talk about is the theory of quantum mechanical description of charges in electromagnetic fields. Okay? So, to do that, I want to begin with the classical theory at some level. Okay? So, classically, charged particle moves under the action of the Lorentz force. And you're going to have to live with me at least one more semester. And I insist on using CDS units. Okay? So the action of the particle moves under the action of the Lorentz force by Newton's laws, where E and B are the electric and magnetic fields, and V is the velocity of the particle, right? We know classically that, so for the moment, right now let's consider static or quasi-static fields. In other words, I'm going to, for the moment, not talk about the coupling to electromagnetic radiation. Okay? We'll come back to that a little bit later. It's more complicated. So I'm just talking about static or quasi-static fields. The electric force is derivable from, is a conservative force derivable from the voltage or the static potential, right? On the other hand, the magnetic field is not derivable from such a potential. Magnetic fields do no work on particles. There's no potential energy. On the other hand, we know it's derivable from a vector potential. And the vector potential has some the funky property that we have gauge dependence. That is to say, if we transform the vector potential by adding to it another vector field, which is itself irrotational, meaning that it is itself arising from the gradient of a scalar, which is called chi, then B is unchanged because the curl of a gradient is 0, right? And so whatever physics there is can't depend on the gauge, because at the end of the day, two different vector potentials lead to exactly the same magnetic field, and according to the Lorentz force law, it's the particle moves under the influence of the magnetic field, and doesn't. So from the point of view of this, A is just an invention of the mathematics. Okay? I'll come back to that important point. Probably this lecture. What it means in quantum mechanics. Alrighty. So we want to write down a Hamiltonian, classical Hamiltonian description, which will then allow us to get the quantum Hamiltonian for the system. So how do we do that? Did you guys study that in your classical mechanics courses when you somehow took that? It's undergraduates probably.
Quantum mechanics, actually.
Oh, you got it in quantum,
Yeah.
but, yeah. Yeah, classical mechanics is out of fashion, it's so 19th century. But, oh well.
Stupid dude.
Yeah. All right, so, well, the way we can do it is to start with the Lagrangian, okay? So the Lagrangian, well, we can't just write down kinetic energy minus potential energy because there is no potential for the magnetic field. However, there is a piece we can write down in the Lagrangian which does the trick. So now how do we do it? So the Lagrangian of the system is t squared minus v squared. The potential, of course, in this case, the potential is the charge times the voltage. So that's minus q. That's fine for the electric piece. But for the magnetic piece, my claim is that I can obtain that as follows. I want to add an additional velocity-dependent piece to the Lagrangian. Okay. How can we see that, in fact, this is the right Lagrangian for that will generate this equation of motion? In other words, we want to have that mx double dot, or we want the Newton's law says that this is the force. So we have to have that. Or in other words, I really should say, no, I want to be careful here, that mx ma is that. All right, well, so if we have a Lagrangian, I can get the canonical momentum. So the ith component of the canonical momentum is equal to the partial derivative of the Lagrangian with respect to the ith component of x dot, right? The q and p. Q is x in this case. So what is that?
Mx dot.
I guess I forgot a half, didn't I?
Yeah.
Well, you just didn't pick up factors.
Yeah, that would be nice. Okay, now it's right. Okay, so now we have mx dot
So
sub I. And then what about that? Well, there's no x dot dependence here, but there is an x dot dependence here.
plus q a sub I.
Right. Oh, and this, of course, is in CBS units. After my diatribe, how could I screw that up? You oversee. A. So I. All right? So, does this give the correct Lorentz force law? Well, according to the Euler-Lagrange equation, the time derivative of the canonical momentum is equal to the partial derivative of Lagrangian with respect to x sub I. Okay? Something is messed up here. Hold on a second. Let me just check a sign here. Great. Didn't load.
What was that down again?
I think you subtract that from the Lagrangian. Minus.
Yeah,
q.
you know what? I think this must be minus sign. Which always, this is something I was going to warn everyone about. Often in this, we're talking about an electron. The electron has a negative charge. And it's not consistent in many textbooks of whether E is a negative number or a positive number. So for example, in Sakurai, when he does this, he says E, but E is less than 0. And it just drives me nuts because I can never remember where this sign is. It's got to be this way. So let's see why.
So you need a big
There's
sign
minus
there.
there, yeah, for P sub I,
I do.
the minus.
Minus Q over C.
Mhm.
Let's see. Let's do it because I'm being bothered, but let's see what happens. Let's see what works because I can't remember because of the damn E thing. Okay, let's explain. Let's see what happens.
Just to make sure,
Yeah.
the Lagrangian is x dot or I dot?
No, there is no chi. I'm sorry that they look the same.
Ah, it's x.
Yes, because chi is a particular choice.
Yeah.
Okay, so this is the position. Excuse me for my bad handwriting. That's x.
Okay.
Chi is not a vector.
Yeah. Dot.
Indeed.
X dot.
Yeah.
That's what it says.
On top of the X.
Oh, the derivative. Yes, x dot.
Yeah.
Indeed. Yeah. Okay, so let's give it a shot. The gradient here of the Lagrangian. So that is equal to minus, or Q times minus the gradient of the scalar potential. Okay? And then I have, according to this, minus right. Right, okay, sorry. I got myself confused a second. So now I have to take minus Q over C, the partial respect to I of x dot sub j, a sub j. Right? That's the dot product. Sum over j. Aha, yes, it was plus. Good. That's what it was. That's correct. So now let me show you why that must be true. So this is what? That's the gradient potential, minus the gradient potential, which is what? Electric field. So this is E sub I. And what about this? Well, this is Q over C xj times this tensor. I know you're doing this right now. In E&M, I peeked. I'm a snoop. And this is epsilon ijk times the kth component of that. Which is nothing more than v sub k. And thus, we get Newton's law. The derivative of momentum, canonical momentum, respect to I is equal to Q vi plus Q over C, the I component of V cross V, or dp dt, which is QE plus QV over C cross V. So, this Lagrangian with the plus sign gives the correct equations of motion. What is the Hamiltonian? Well, to do the Hamiltonian, you have to do the Legendre transformation, right? To get the Hamiltonian, I have a Lagrangian expressed where x dot as a function of p and x minus x dot p. Okay? That's the recipe from classical mechanics. You plug all of that in, and you get the following. This is 1/2 P minus Q over C A plus Q. This is my Hamiltonian squared. It's not an operator yet. All right, so what are some important points to note here? One important point to note is right here. The canonical momentum does not equal the kinetic momentum. The kinetic momentum is mass times velocity. But the canonical momentum has this funky additional piece from the vector potential. It is the difference between this and this that is the kinetic momentum. And that's what appears in the kinetic energy. Okay? All right, so given this, this is now a function of x, this is a function of position, we can write down the quantum Hamiltonian for a charged particle moving in a quasi-static electromagnetic field. Let's do it over here. So now P goes to P hat. Position goes to position hat. And my Hamiltonian is thus the following. Where Pi xj is now satisfies the quantum canonical commutator. Okay. Note, importantly, it is the canonical momentum that must satisfy these commutation relations, not the kinetic momentum. The kinetic momentum which is sometimes written as pi, is the difference between,
Should it be XP?
what are you talking about?
The commutation. Should it be X of P, the IH bar?
Oh, yes, thank you. You mean the order. Yes, thank you. Absolutely. Commutative of x and p. Thank you. That's the kinetic momentum. In fact, the different components of kinetic momentum don't commute with one another, because x and p don't commute. In fact, you have a homework problem for that, to think about that. But the components of canonical momentum do. Yeah,
I'm sorry, so where, it says where X, the commutator X and P, so is that P there,
that's canonical momentum.
so that is, okay.
That's a canonical momentum. And the canonical momentum is the generator of translation. Okay? And it has the representation as the gradient operator. It is that operator, because what we discussed last semester, if the generator of translations in space follows from this commutation relation. And because the canonical momentum satisfies the commutation relation, it is the generator of translations in space. And in the position representation, the thing that is the translation in space is the derivative, the gradient. Okay?
So if there's no magnetic field, then they're just the same, though?
They are the same.
Okay.
Yep.
Okay.
All the craziness is all about the magnetic field.
Okay.
At least in the quasi-static case. The vector potential shows up again in radiation for the vector field as well. But we'll leave that aside. Okay, so since my notes didn't load, I should remember what I wanted to do next. And let me say the following. Let's look at the representation. In position. Space. So let's say I have the time-independent Schrodinger equation. Okay. H psi, E psi. Let's again write this in position space. Okay. Is equal to d psi of x. All right, so what do we got here? Well, when I write that out, what I get is 1/2m, the position representation of the canonical momentum is the gradient minus q over c a of x squared plus q, the potential acting on psi, is equal to d psi. Okay? So that's the Schrodinger equation, including, this is what we would just call V. But now I have, because of this vector potential, I have this craziness. Now, here's a very important point. We said, in the front board, that we should be able to make a gauge transformation, change the vector potential by adding to it the gradient of the scalar without changing the physics. That has to be true. So what does that mean here? How do we account for gauge invariance here in the Schrodinger equation? Because obviously if I change A by adding to it the gradient of chi, well, it looks like I've changed the equation. Okay? So the only way to deal with that is to say that the probabilities of the measurement, of any measurement I can do, cannot depend on gauges. Okay? That's to say the physics must be independent of the choice of gauge. And what that means in quantum mechanics is that the outcomes of any measurement have the same probability for any gauge. Okay? That's what we insist. So when we change the gauge, we can't change what we're going to find when we do a measurement. Okay? So how can we ensure that that's the case? The way we ensure that case is that to show that a gauge transformation is equivalent to a unitary transformation on everything. So this implies that gauge transformations are achieved via unitary transformation. What do I mean by this? So this is like we had the Schrodinger picture or the Heisenberg picture. It didn't matter which picture we used, we would get the same measurement outcome probabilities in either picture, although the two pictures were related to one another unitarily. So I claim that there is a unitary transformation I'll call U sub G, which achieves a gauge transformation. And what that means is that I let psi become psi tilde by just unitarily transforming it. And I let my observable go to observable tilde by a unitary transformation. Okay. If I do that, then the matrix elements of O are the same in any gauge. That's to say, the matrix elements of O tilde are the same as the matrix elements of O hat in the two gauge. That is to say, if I look at O between two states, and I shove in here a U dagger, and a U dagger, U like that, that's the same thing, right? And that's equal to that. So if I transform the operators and the states by these unitary transformations, I don't change the physics. So now I want to show you that there is a U that does the job, that achieves a gauge transformation, and that will have profound implications for fundamental physics. Yeah?
Actually, this is more than expectation value.
Yeah, I'm sorry, it's matrix elements, right? Any matrix element is fine. That's true. If I do a unitary transformation and everything, then every matrix element is the same. And therefore every prediction of probabilities will be the same. All right, so what is the U? The U is simple. So claim U, G, is equal to e to the minus I chi of, I'm going to have it, E over, or Q over H bar C chi of X. So what I claim, I claim that this achieves its gauge description. Yes, sir.
What do you mean by change the gauge transfer?
Well, I'm showing you.
When you apply
What I mean is that when I do this transformation on the Hamiltonian, it will take A to A plus the gradient of chi. Okay? So let's try that. So let's look at the this is U, H, oh, let's do this. So I'm going to look at this guy. U dagger. Okay, so now I'm just shoving in my U dagger U's just like before. That's the same thing as we had before. Okay. And what do I get? Let me write this up before, excuse me, I think it'll be easier. I don't have my notes and I realize what I really want to say. So let's look at this, which is everything in the new gauge. This is my new Schrodinger equation in my new gauge. Okay? And now let me look at the position representation of this. Okay. So, what does that equal? So this is U, G, H, U, G dagger. U, G psi is equal to E sine of X.
Are you looking at it in X or the X code?
Doesn't make a difference because that's an overall phase. Let's look at this. Plugging that in, what I get is a transformation that looks like this. 1 over 2m h bar over I, the gradient minus q over c a of x. Then I have my e to the I q, or even minus I q over h bar c chi of x acting on tilde. And I have that
Should it be a
phase.
plus I on that side since it's the dagger?
Blah, blah, blah. Blah, blah, blah. Let's see. You're right, it is the dagger. And the question is whether this is a plus or a minus, because it's gotta be a plus. It's gotta be a plus. Yeah, science. So that's what that phase is, acting on this square.
Do we need another E on the other side?
We do. That's back out, e to the I q over h bar c I of x. All right, so now I move this through, move it in, and the gradient comes down here and gives us the gradient of chi. So we end up with minus q over c a plus the gradient of chi squared acting on psi tilde is E psi tilde. So this unitary transformation does the job. It changes the vector potential by adding to it the gradient of a scalar. But I want to conclude with one important point here. And that is, what happened to psi tilde? What is psi tilde? Because that's actually the most important point. Well, psi tilde of x was just the x representation of the unitarily transformed psi. And that did nothing more than place a phase, which has some sign that I'll get straight next time, so I will pardon me about the sign of it. Which is that, right? Now, here's the important point. We said that the overall phase of the wave function was irrelevant, right? And in this case, we do have an overall phase, but it's a spatially dependent. So it's a local phase. It's a different change in the phase of the wave function at every position in space, depending upon what the local value of the gauge function chi is. Okay? It must be the case, it doesn't matter that we did that, it must be the case that we don't change any probabilities, even though the phase is varying with one position, it's still an overall phase and any probability. But we can turn this on its head. What quantum mechanics tells us is that because it must be true that psi tilde has the same predictions as psi, there must be a vector potential. That is to say, when we do this, we add a gradient of chi to the system. So if there was no vector potential, all of a sudden there is one. The fact that quantum mechanics is invariant under a gauge transformation. This is a gauge transformation on the wave function. Because the quantum mechanics must be invariant under a gauge transformation, there must be a vector potential. And this is the foundation of modern quantum field. This is what's known as a gauge field. That is to say, we can understand that there must be a field that the charges coupled to the vector potential. In fact, the vector potential is the whole story when you get to that and beyond statics, the dynamics. The fact that the quantum mechanics is invariant under this says that there must be a coupling to an electromagnetic field, and that is known as gauge fields. We'll conclude there, and we'll pick up with some more craziness, talk about Berry's phase and talk about things coming up, and coupling the Harnack-Bohm effect.